This is an exciting video, and I've said this in the last video, but I want to say it again for why it's an exciting video. Because I'm showing off a strategy that is used multiple times in math, right? We look at a specific example and we say, can we generalize this at all? Is this going to be a pattern? And then we use that kind of guess to kind of try to get a solution, try to be able to extrapolate more things. So we solved a specific example using other methods, and we're going to try to say, can we generalize this for more things? And that's a pretty powerful method. Some questions that we're going to ask is, is it always of this form? Is there always going to be a t here? If the first vector is always our starting vector, our initial condition, what does that second vector look like? Is the second vector always so nice? So in order to do that, we're going to consider the differential equation dy dt equals a times y, and we're going to specifically look at specific systems with lambda a repeated real eigenvalue. Also, am I being redundant? Is it possible to have a repeated eigenvalue that is not real? I am being a little redundant here, because if it's complex, remember they always come in pairs of complex conjugates. But anyway, let's say we have this, and we're going to say that v naught is going to be our initial condition, x naught, y naught, and we're going to be really curious about whether we can generalize this. So we're going to look at the function y of t equals e to the lambda t times our initial condition plus t e to the lambda t times some vector v1. We're not going to actually make any assumptions on what v1 is. We're going to say, could this be a general solution? And if so, what do we need for v1? And again, we're sort of abusing notation a little bit, and I want to be very clear. We're not assuming these are eigenvectors. A lot of times we do use like v1 and v2 for eigenvectors, but we're not doing that right now. So be very careful. We're not assuming that. We have an eigenvalue. We haven't talked anything about eigenvectors yet for this specific video. We have found eigenvectors for repeated real roots. You did that in the last video. But again, just like over here, these were initial conditions and this was something else. These weren't the eigenvalues. Or sorry, these weren't the eigenvectors. The eigenvectors you found elsewhere, and we used them to create this. Anyway, we found one eigenvector because we only had one eigenvalue. Okay, so is this a solution? That's what we're going to ask ourselves. And of course, to answer that, this should be a question that you know how to answer. Something is a solution to a differential equation if it makes the equation true. If it makes both equations true, if you have a planar system. One equation needs to make it true. Two equations, it needs to make them both true. So let's look. What is the left-hand side of this equation? The left-hand side of this equation is dy dt. We can calculate that, no problem. Well, maybe a little problem, but let's see how it goes. What is the derivative of y with respect to t? Now remember, these are constant vectors. This is our initial condition, and this is some other constant vector. So the derivative of this with respect to t, there's only a few t's in here, right? These are the only things that depend on t. These are the only, oh, we're going to have a product rule. Oh, okay. So derivative of this with respect to t, again, v naught's a constant. So it's just going to be lambda e to the lambda t times v naught. And then we need the product rule for this next one. Derivative of the first function times the second function plus the first function times the derivative of the second function. Okay, that's what we've got. Can we clean this up a little bit? I think so. Everything has an e to the lambda t. I see that right now. Let's factor out an e to the lambda t and see what we get. We're going to be left with lambda v naught. Actually, we're not going to end up wanting to do this. But I know that. I'm not, no cheating, no cheating. I'm going to show you what I would naturally do. Lambda v naught plus just v1 plus lambda times t. Oops, we factored that out. Times v1. Anytime you're factoring and you're a little nervous whether you did it correctly, remember you can just distribute and make sure that you are correct. This is just that without the e to the lambda t. This is just that without the e to the lambda t. And this is just that without e to the lambda t. Okay, so that's the left-hand side of this equation. Now we're going to need to look at the right-hand side of the equation. And actually, I think this will be okay, just not what I expected. So the right-hand side of this equation, all right, we're going to need this later. Let's just steal this for now. This is the left-hand side. What's the right-hand side? Again, we're trying to make this system of differential equations true. The right-hand side is just a times y. What is that? Well, the matrix A, we don't know it. You could write A, B, C, D, but let's just keep it as A. But we do know what y is. Specifically, we said y was this guy. So let's write that down. Okay, so y is going to be e to the lambda t times v naught, our initial condition, plus t e to the lambda t times v1. And again, be very careful. We're not assuming we have any eigenvectors here. So if we had eigenvectors, that'd be really nice because a times the eigenvector is the same as lambda times the eigenvector. And that would sure be really nice to have right now, but we don't. So I'm going to try, I want the left-hand side and the right-hand side to be the same because I want this to be a solution. This is our y. I want y to be a solution. I want these to equal each other. If I'm trying to show two things are equal to each other, I should try to make them look the same. So what I'm going to do is I'm going to distribute that a and actually factor out the e to the lambda t. So right, a I'm putting into both, and e to the lambda t I'm actually taking out of both. So I'm just switching things around a little bit because I want it to look like this. So when I do that, I get e to the lambda t, and I'm left with a times v naught plus t times a times v1. Okay. So I need these to be equal. When are they going to be equal? Well, e to the lambda t is always going to equal e to the lambda t. This is never 0 either, so we never get any weird funny business. This needs to be true for all t. All right, we want the left-hand side to equal the right-hand side always for all t. This is my upside down a, means for all. I'll write that down. So when is that going to happen? Well, everything with t's need to match. Remember when we were doing power series? Right? Everything with t's needs to match, and everything without t's needs to match. So what we need for this to be a solution is for these things to be equal to each other. So we need a times v naught to equal lambda times v naught plus v1. And we also need a times v1 to equal lambda times v1. Oh, interesting. There's only 2 times when this happens. When can this happen? Well, when v1 is an eigenvector, or we haven't talked about this much, but if it's the 0 vector, this also works. And notice what happens in either of these cases. If v1's an eigenvector, let's just move things around. If v1's an eigenvector, we know what it is. If v1's an eigenvector, it's going to be, let's solve for it. We get this. Ooh, can't we rewrite this a little bit? These are 2 vectors subtracting each other. This is a minus lambda I times v naught. So this is all we need. we have a solution of this form, and it's always going to be a solution as long as one of two things happens. Either that second vector is 0, in which case the first vector has to be an eigenvector, right? If v1 is 0, then v0, our initial condition, has to be an eigenvector. So that's one possibility. Or v1 is the eigenvector, and we can find the eigenvector, remember, and we know that v1 is going to be related to the initial condition in this form. All right. So we've basically found the general solution. Let's formalize that with a theorem. Suppose that dy dt equals a times y, your favorite thing to write in this chapter, is a linear system of ordinary differential equations with repeated eigenvalue lambda. Again, it's real. And only one line of eigenvectors. So we're looking at only one straight line solution, one eigenvalue, this degenerate case, this sort of borderline case between spirals, complex eigenvalues, and more traditional sources, sinks, and saddle points, okay, which is when you had two distinct real eigenvalues. Remember, we're in that kind of liminal zone, this transition zone, this border zone, okay, this borderland, if you like video games. It was bad. Not my best jokes today. So let's say that we are assuming this. Then here's the general solution. The general solution of this is just y of t equaling essentially exactly what we wrote at the beginning of this video. It's e to the lambda t times our initial condition plus t e to the lambda t times some other vector, and I'll tell you about that vector right now. So again, let's formalize this, right? V naught is our initial condition. And what is V1? It's going to be what we found. V1 is going to be A minus lambda I times V naught. And notice I gave you some cases, right? I said V1 could be 0. But if V1 is 0, you're going to see, like, we can multiply things out and you're going to find that V0 is fine. It's just going to be an eigenvector as a result. So we'll summarize that as well. Right? If V1 equals 0, then V0 is an eigenvector. And we have a straight line solution along that eigenvector, of course. Otherwise, V1 will be our eigenvector. All right. So, there we go. We got a theorem for a general solution. I wish I drew nicer boxes. Watch this. I'll draw straight lines. Wow, look how good my straight lines are. All right. It's not that good. It's not that good. Anyway, here's our theorem. This is what we're going to use to find some things. And again, here's our general solution inside. Now, this is, you have to be a little careful here. This entire chapter, what have we done? We have found two solutions. And then we said, oh, if these are linearly independent, our general solution is a linear combination of these two solutions. Now watch out, because these are not two solutions. Okay? Sometimes we might have solutions in here, but in general, these are not going to be two solutions. So watch out for that. That's a little bit of warning. And we might talk more about that in future videos. But currently the dog's going nuts. You have your theorem, you have everything you need to know. We'll revisit our example with some extra practice in the next video. Bye-bye.